So let's talk about some Pythonic conventions and talk about some more basic Python syntax. So let's talk about what it means to be Pythonic. This is essentially a term which helps define the different types and styles of coding that exists and that you can use with Python. And essentially, we designate things as Pythonic when they are the best styles. Now, that type of definition of how you can code in Python it's an ill-formed definition, and it changes as the language matures, as more developers interact with it. So at a very high level, Pythonic code is something that is simple and readable and uses dynamic typing when possible. Or, to quote Tim Peters, if you type import this into the Python terminal, you'll get a poem essentially by Tim Peters, which is called The Zen of Python. And it basically explains what it means to have Pythonic code. He has all of these things where beautiful is better than ugly, explicit is better than implicit, special cases aren't special enough to break the rules, although practicality beats purity. It's basically all of these types of one-offs and not very descriptive and not very specific things that make code Pythonic, but that doesn't mean that they're not useful, right? So even though this is kind of a quirky way of introducing what is and what is not Pythonic, the idea here is that you want code that is very intuitive and easy to read. And that's really what Python was invented for in the first place, is to make something that is readable code. Because most of the time your code is read, very few times is it written, right? So the Pythonic conventions that we have, well, really, there's too many to go over. Yeah, and if you want to look at all of the different things, you can look at part of the legacy Python, the PEP8 conventions that we have right here. But to go over a few, variable names should be done all in lowercase and with underscore to separate the different words that are there. So this is a Pythonic convention to make your Python code more readable. So this is my variable would be named this underscore is underscore, etc. Until you've spaced everything out. It's all lowercase. Use indentation to increase clarity, right? So when you can indent something in an if statement, go ahead and indent that and put it in there. Indentation is king in Python. So typically what we're going to use here is 4 spaces or a tab, right? And so those are the exact same size. There are some versions of Python where you can get away with 2 spaces as a tab. Don't do that. Essentially, to keep it Pythonic, we want to keep things as consistent as possible, and so indentations should be 4 spaces or a tab. Put 1 space before and after an equals or an assignment sign, so x equals 5, and space mathematics well, which means, go ahead and put spaces where it makes sense. That typically is around orders of operation where you might have parentheses, right? So here, x times x plus y times y, exactly the way that you might think about it inside of your head. Right? There are many, many more Pythonic conventions, such as when you do classes should be all uppercase. Not the whole thing uppercase, but they should be capitalized, right? And you should really adhere to good spacing of your code, right? So don't do too many spaces between lines. 1 line of space is probably enough between sections of code. So one of the things that'll make your code more Pythonic is more intuitive and more readable is the use of dictionaries. And dictionaries are defined in Python like they are in almost every other language. Essentially, they are a key value or key array pair. So in this example here, I'm defining something called numlegs. And the syntax for defining a dictionary is to have an open and a closed curly brace in the exact same way that you would have brackets to define a list. Now, what we will do is when we create this dictionary, the keys will be on the left side of the colon, and the values will be on the right side of the colon. So I'll say numlegs at the dog would be equal to 4, and numlegs at cat would be equal to 4 as well. Numlegs at human, if I were to access it, would be equal to 2. And the way that we actually access into these dictionaries is exactly how you might think. We would say numlegs at the dog or the human in the exact same way that if this were an array, these would be 0 or 1 or 2. It's basically a key that tells you how to get to the value that's in that dictionary. So if we look at the format for a dictionary, these are the keys that we have. Those are basically where we're actually pointing to the different containers that we have inside of our dictionary, right? So these point to the container that has maybe an integer or a string or a float or a list that can hold anything in the exact same way that a dictionary could hold any type of value or array inside of it, right? These are just generic containers, and the keys tell us what can be in there. Now, there's no hard and fast rule on what the key inside of a dictionary needs to be either. So it could be a number, it could be a string, it could be anything that's immutable you can put inside as a key inside of a dictionary. So for this example, if I were to say dog and human right here, I would get 4 and 2 on the output of numlegs right here. And if I were to print out numlegs, it would print out in very, very similar fashion to what I have before, except the keys are going to be in a slightly different ordering. It might be a random ordering. When we, if we want to add a key into a dictionary that we've already created, it's actually quite easy. We simply just create the new key that's right there. So numlegs at the human would overwrite the value that is inside of numlegs that we have right here. Numlegs at the bird, that key didn't exist before. Because it didn't exist, it will add a new key inside of this dictionary, so bird right here, and set it equal to 2 and some wings. Numlegs at the 45, again, this is not a string, it is an integer. This 45 is a key, and it says a key that is not a string. That will be the value that's inside of it. So if I were to print out numlegs now, I would get, I could see bird, 45, dog, and human, right? And that's because I've deleted numlegs at the cat, and that's the way that you actually say this is DEL numlegs at the cat. And if I print it out, I'll get it here. So that's dictionaries. They're pretty easy to use, and they're actually extremely useful for a lot of the abstract data types that we want to use. Actually, we're going to incorporate a dictionary into our calculator example. So let's talk about a couple of our abstract data types, such as sets. Sets are extremely useful in Python as well. Let's say we have a basket right here, and inside of baskets we have apple, orange, apple, pear, orange, banana, right? So we have a couple of apples, a couple of oranges, pear, and a banana. If I wanted to create a set out of that basket, I can simply use the Python set function right here. So I'll create a set out of this list of items. And now fruit, if I look into it, right, it's basically like creating a basket and throwing things into it. The set will only have the unique items that are inside of that basket we have right here, right? And so set has an orange, pear, apple, and banana. It's the unique items that I had in there. Now, if I print is orange inside of fruit, I get true. If I print crabgrass in fruit, I would get false because that's not part of the set that I have here in fruit. Okay. There's also some easy operations here. If I say A equals a set of 45, Eric, 4.0, and 5.6, or 5.6, it's going to give me a type error. And the reason it says that is because this 5.6, this list right here, that's not something called hashable, right? So a list is not hashable data because that list is mutable. I can change the value of this list 5 and 6, and that is not something that I'm able to use inside of a set, right? So all of the things that I put inside of a set need to be things that are immutable, right? So let's give a couple of examples right here. Let's create two sets. Set A is going to be a set of letters right here, abracadabra. It's just the unique letters in abracadabra. And B will be alakazam. Why not? I'm also going to add an exclamation point to A right here. So I've added that into the set. I can do various very intuitive operations upon that set, such as just printing out A. I can see, oh, here are all of the unique characters, right, that were in abracadabra with an exclamation point. I could print out the letters that are in A but not in B, right, with the minus, the subtraction sign, right? So I can see this. I could print out the letters that are in either A or B, A and B, or I could say those that are in A or B but not both, right? And so this gives me basically an exclusive OR operation, right? So those are sets. Sets we can change on the fly. If you ever needed to create a set that wasn't mutable, that you wanted to stay the same, you could also create immutable sets using something called frozen set, right? So this is a set that after you create it, you cannot change it anymore, right? So if I were to, I'm going to create an immutable version of the A right here by saying frozen set A. And then if I tried to add something to it, say E to the immutable set, I would get an error. Tell me that, this is an immutable set you can add. So the reason that I might want to do this is if I create a frozen set, that means it's immutable. That means I can actually use that set as a key inside of a dictionary if I wanted to. And that could be a potentially very powerful data type that you might use later on. If something is immutable, you can always go into the set and see if it exists, or immediately kind of hash that value out of it and access the value very, very quickly. So organizing code is going to be really, really important for some of the things that we do, especially when we get into more advanced functionality and operations that we want to repeat over and over. And the way that we do this in Python is through functions. Now, we've already defined very, very simple functions, but let's go in and actually look at some of the functions that we can define in Python and be a little more explicit about what we can do with functions and look at the power that functions have. So not just, defining an input and some kind of output, but let's do a little more. So here's a very, very simple example, show data, where we just print data. But we can also redefine show data to basically take in as input data, and then take two more optional arguments, x and y. And basically what we're doing here is we're saying, oh, x and y have a default value. If someone does not pass in the value for x, they do not pass in the value for y, I'm actually going to set them equal to none right here. None type is essentially in Python. Just like we had something returned from a function, if we get to the end of the function we haven't returned anything, it'll return none type. But we can explicitly say that x and y are none right here. And now we can print data, and if x is not none, we can print it, and if y is not none, we can print it, right? And so now we can define a bunch of operations right here where we show data, and we give x and y as optional arguments. Now, one thing that's interesting here is when I give these arguments names right here, x equals, y equals, I can actually say y equals and x equals inside of the function itself. And it doesn't matter what order I place them in, y is explicitly set via a cool y value, a cool x value. And lastly, something that's really, really interesting with functions is that we can have multiple returns, right? So if I say get the squared and the 10th power, some function I'm defining, I can say x squared and x to the 10th and return both of those operations as a tuple, right? So now I'm returning this output as a tuple, and that tuple can be of any size that I want, right? So now if I look at the outputs of all of these, I can see that they're doing exactly what I have here. I get my default x values right here, and if I square and take 2 to the 10th power, I get 4 and 1024, which is really kind of a motivating and very concise syntax for being able to use Python and making my code more readable, more intuitive to look at. So let's revisit the calculator example that we had last week. And again, I'm in the exact same IPython notebook that we had from last time, where we had created this, essentially this calculator where we defined perform operations, and we defined this value of is operation. Let's go in here and let's change the way that our calculator works. And specifically, let's use dictionaries to define the operations that we have. That's going to make our code a lot more Pythonic. So here's the first thing I'm going to do. I'm going to define this thing called an operations list. And really it's an operations dictionary of things that we have. And the keys are going to be the symbols that we might use as operations. And the values are actually going to be functions, right? So I told you that you can put anything inside of a list or a dictionary, and I meant anything. So this operation right here, I'm importing operator, which is basically a module of all of the different basic operations that I can do in Python. And I'm going to import it as OPER. So now anything that was in this module, I can get access to using dot notation. So plus right here, that's just an operation where it's oper.add. Oper.subtraction, multiplication, division. I can take something to a power, and we're going to add another operation to our calculator, modulus. So now that operator list is no longer a list, it's actually a dictionary, I'm going to define my is operation to say, hey, the value right here, when I want to know if this value is supported for my calculator, I'm just going to say if the value is in operations list, all of the keys. So if it is in these explicitly defined keys that I have right here, these keys, then I will return true. Otherwise, it's not something I support right now, I'll return false. Everything else basically stays the same, except for my perform operation block. And actually, my perform operation block has gotten extremely simpler. And the reason for that is this. I'm going to import OP, and I'm going to import the values that I want to perform the operation on. It's a tuple, just like we had last time. Now, this is going to be a little bit funky, but stay with me. This operation is a string that I want to perform. I'm going to go into my operations list, and I'm going to grab the function that is at the value OP right here. And that's what this does. So it goes in, and out of the dictionary, it grabs a function. Actually, I could make this more explicit if I wanted to. I could say this function is equal to operations list at the OP. Right? And so that would save this into some arbitrary function. Is now saved there. And now this function, I can actually pass functions around in Python all that I want, in the exact same way that I can do in C and C++. Right? So now I can actually just say func right here. So I've defined this new function, and I'll give it the inputs, which is values at the 0 and values at the 1. Right? And I'll just return what the output of that function is. Right? And so this is a very, very compact notation now, because my dictionary defines exactly all of my operations and how I represent those operations. So the code that I have down here doesn't really change at all. I'm exactly going through, hey, if it's an operation at the very end of the evaluation clue, get the operation, get V1 and V2, and now perform that operation given what the operation is and the values that I've popped off of the list. So if I run this, we can say something like 5, 6, and now if I enter plus, it's going to take plus, go into the dictionary, grab the correct function, and use it immediately, right? So now any function that has 2 arguments as the input, I can immediately just add that into this list, this dictionary right here, and it immediately will work. And the only lines of code that I need to change are right here. So this is now a very, very scalable calculator example, right? Now let's go in here and let's see if we can make this code even more Pythonic. But first, let's learn about how to make things object-oriented.